Good morning once again. We're getting into our next session. We've got 3 presentations. Before we start, my name is Kaemete Tsotetsi from the dtic. Fortunately, I'm not the one who's doing the presentations. I'm sure there will be Elvis here, my colleague. If there was going to be any questions, I was going to feed them all of those questions to her. But yeah, I'm just a moderator. We've got David Willward, who's going to give us a presentation on blue hydrogen as an interim phase of the just transition. Is it feasible, a proposition for South Africa? The second presentation will be by Elvis, Avenyo, and others. But Elvis is here, will be doing the presentations on the determinants of technologist adoption in South Africa manufacturing, evidence from a firm-level survey. The last presentation will be a liquid fuel in South Africa, Sasol coal to liquid case study by Kathleen Bergh. She'll also be online. So on that note, I'd like to welcome Professor David Walwyn. He's a professor in a graduate school of technology management at the University of Pretoria. His research interests cover sustainability, transition, renewable energy, science and innovation policy, research management and industry localization, the latter with a particular focus on vaccines, renewable energy technologies and pharmaceuticals. He teaches courses on engineering economics, project economics and circular economy and energy value chains. He supervises at least 15 master students each year on the management of technology and innovation program offered by University of Pretoria. Has 3 PhD students. He has published widely in area of science and technology policy, research management, and health and science biotechnology. The details can obviously be found on Google Scholar and ResearchGate. Professor Walwyn has a BSc Chemical Engineering from the University of Cape Town and a PhD in Organic Chemistry from the University of Cambridge. He's a member of the Academy of Science and Science of South Africa and associate editor on the International Journal of Innovation and Technology Management. I'd like to welcome Professor David Walwyn online to give us a presentation. Over to you.
Thank you so much, Kaemete. And I just want to check, first of all, whether you can hear me properly.
Yes,
yeah, okay, you can hear me. Perfect. All right. So I'm talking to you from somewhere in the Western Cape, a place called Riebeek West, which is in the Gamadulas, you could say that. And so if my connection becomes unstable, you can just interrupt me and say, we can't hear you properly, or yeah, we'll make another plan. So I'm going to start sharing my screen. Blue hydrogen as an interim phase of the just transition, is it a feasible proposition? That was such an interesting session this morning, completely absorbing, very controversial in some aspects. And I hope to be able to continue the interest and enthusiasm for a just transition. But let's see how we go. So I'm going to be talking about this question of blue hydrogen, whether it is a suitable interim strategy. It fits in the conference theme, obviously, and I'm very mindful of the presentations yesterday about this, the importance of aligning industrial and energy policy, and perhaps you just need to have an industrial energy policy full stop and not create a separation between the two. But my main proposition in this talk is blue hydrogen could be manufactured as an interim measure to retain operational coal mines, whilst partially decarbonizing energy systems. And it's that statement that I will be interrogating. It's not a hypothetical question. Those of you who are familiar with the Hydrogen Society roadmap will know that in that roadmap, there is this interim period. So the idea is to prioritize, and I'm quoting from the roadmap, prioritize blue hydrogen relative to green and gray over the period 2021 to 2050, driven by the need to preserve asset value, conserve employment, and allow the slow introduction of socio-economic adjustments. So that's the strategy. And I think that's exactly the statement that I want to interrogate, and I will allow you to make up your own mind on the subject. But in the process, I'm going to be covering, first of all, what is blue hydrogen for those who aren't familiar with the different colors of hydrogen. How does carbon capture and storage work? So a little bit of process engineering, chemical engineering in the beginning, and then we'll do some techno-economics, and I'm going to introduce you to levelized cost of hydrogen, which the mullahs think is up to maggots. But they talked about levelized cost of energy rather than LCOH. But I'll talk a little bit about that, and then the political economy consequences of following a blue hydrogen strategy. And I'm going to be in that section talking about multi-level perspective. I just want to check with the chair how much time I've got. You didn't say in the beginning.
Okay, I saw about that, Prof. You now have 13 minutes. 13.
13. Okay, brilliant.
Yeah.
So we'll make it in 13 minutes. Simon covered this yesterday, Professor Roberts. The hydrogen economy could be very pervasive across the whole economy. It could be used as fuel for transport, so mobility and electricity. It could be used as heating in industry, and we heard about decarbonization of the cement sector this morning. It could be used in heating of buildings, residential and commercial. And of course, it could be used as a chemical feedstock. So multiple uses for hydrogen and green hydrogen across the hydrogen economy. And what are the different colors and what do they mean? So those who are not familiar with this, hydrogen is very colorful. The black hydrogen comes from coal without carbon capture and storage. Gray is from oil and gas without CCS. And then blue, which is what we're talking about today, is from fossil fuels, regardless of whether it's coal or oil or gas, with carbon capture and storage. And so that's the issue that's on the table in this presentation. Pink then is hydrogen from nuclear energy via hydrolysis, turquoise, etc. So without going into it in any further detail. And we've talked quite a lot this morning already about green hydrogen. So how does the blue hydrogen process work? And I've got here this is what in process engineers call a block flow diagram. And I apologize if you can't properly see the writing here now, but I will explain to you very briefly what happens. So to make blue hydrogen, what you do is you take coal or oil or gas, and you first of all, it's a process called steam reforming or gasification. And in that process, you inject steam and generally a little bit of oxygen into the mix. And you form this thing which is called syngas. So it's hydrogen and carbon monoxide. And that gas then goes into this reactor here. So these are different reaction steps or blocks in the process. And in this is the well-known step, which is the conversion of carbon monoxide into carbon dioxide and more hydrogen in what's called the water gas shift reactor. So we have gasification followed by then the water gas shift reactor, and then we have CO2 removal. So this is the carbon capture step here, and then that leaves the hydrogen in the this would be blue hydrogen in the final step. Now, the most important point about this process is that the carbon dioxide is formed not just in this step here, which is the gasification step, but you also have to generate the steam. So you have to supply a large amount of heat in the first step, and that heat comes from essentially from fossil fuels in most of the present processes. And so there is a carbon dioxide emissions as a consequence, first of all, of the gasification of your fossil fuel, but secondly, as a consequence of the provision of heat into this first step. So what commercial facilities are there at the moment for CCS? And I'm going to explain a little bit about CCS. First of all, there's this, most of the carbon dioxide that you might buy if you were to go to the supermarket and have one of those refillable carbon dioxide cylinders, that comes from fermentation off gas. So it's the product of the alcohol industry. And I worked on such a plant in 1985, believe it or not, that's a long time ago. And essentially what you do is you take almost pure carbon, it comes off the fermentation vats, and you put that through activated carbon and then into direct compression, and that is then traded. The second alternative in CCS is this, that diagram that I showed you on blue hydrogen. So it's the gasification, and you essentially form a syngas or a gas stream, which is about 50% carbon dioxide. And that carbon dioxide can be removed in various processes, but the most common is a process called rectisol. And rectisol is a low temperature methanol process where the carbon dioxide is absorbed into low temperature methanol. And I worked on a facility that was using that exact process in 1978. So even before 1985, when it was used by AECI, a company called AECI for ammonia synthesis. And then the final one is flue gas removal, carbon dioxide removal from flue gas, where the carbon dioxide is at a much lower concentration, about 20%. It's much more challenging to absorb the carbon dioxide, and it's done with amine absorption. So first of all, there's some reservations about this step. And firstly, there are no commercial flue gas CCS facilities which are operational at full scale. And most countries are unprepared, as I say here, for the deployment of CCS. And if you want to see further information on this, go to the site that's given here, which talks about the readiness index of different countries. So in the production of blue hydrogen, as I indicated, there are two carbon dioxide sources which must both be treated in order to conform to the requirements of blue hydrogen, which would be hydrogen production from fossil fuels with carbon capture. And the one is the steam reforming step, which I said is 50% carbon dioxide, and you can remove that carbon dioxide with Rectisol. But the other is flue gas. So how do we treat flue gas? And this is shown in this. This is not a block diagram, it's an engineering line diagram. So here's some more process engineering for you. But essentially what happens is you have an absorption step, which is the first column, and then you have a stripping step. And so the flue gas comes in at the bottom of the absorber, and there's this counter current circulation of an amine. An amine is basically a liquid absorbent, which absorbs the carbon dioxide. And typically you get about 85 to 90% carbon capture. So first of all, it's not 100% carbon capture. You still have some carbon emissions. And if you're using gas from gasification or from the steam reforming step, you also get methane emissions at this point, which are very deleterious. Methane is an even more dangerous global climate consideration. So it slipped my mind for a second, but I'll come back to it. And then the Rectisol goes through a stripper column where the carbon dioxide is stripped out of the liquid, and it is then available in a gas stream. The question is now, what do you do with all that carbon dioxide? It's not such a simple problem. So green hydrogen through steam reforming, as I said, is well established. That process for carbon capture by Rectisol is well established. It's a commercial process and has been for a long period, but from flue gas, it's a big problem. And the flue gas issue is that, first of all, there's an efficiency limit. There's, as I said, 13% release of carbon, some fugitive methane if you're using natural gas. It's expensive, and then where can you store it? Now, we have had in South Africa an initiative to look at carbon collection and storage since 2010 approximately. And their conclusion of that, of the work of the SARChI, I think it is, I'll show you in a minute, is that it's a non-trivial engineering problem how to collect the carbon dioxide from these various emitters and then transport it to a subsea depository. So the South African Center for Carbon Capture and Storage identified possible sites around South Africa, all of them offshore, all of them very expensive to access. And there are 5 possible sites here, and these are all as a consequence of certain geological formations. So the further information on that is published in this document 2014 in Energy Environmental Science. And it just says that safe and secure carbon dioxide storage has been demonstrated. So we know the problem can be solved so long as you are prepared to pay the money to pipe the carbon dioxide into those areas and then push it underground. Now I'm going to switch tack slightly and talk about the techno-economics, which is this issue of the levelized cost of hydrogen. I am a firm believer in levelized costs, and notwithstanding 5 minutes.
Yes.
5 minutes. Notwithstanding the reservations of the mullahs this morning, I think it's an extremely useful parameter, and it can be adjusted to incorporate some of the aspects that they were critical of. So first of all, it's a techno-economic approach, and the levelized cost of hydrogen is simply the sum of the discounted costs for hydrogen production over the lifetime of the system divided by the sum of the discounted value of the hydrogen produced. And it gives you these kinds of values. So this is a comparison of gray hydrogen, blue hydrogen, and green hydrogen in the years 2020 or 2019, 2030, and 2050. And some very important points. First of all, the cost of gray hydrogen production will go up, and this is as there are increasingly stringent requirements for the control of emissions from gray hydrogen facilities. And those will be expensive to implement and will increase the cost of the LCOH of gray hydrogen. Secondly, blue hydrogen is not expected to change very much, and that's a very important consideration in any strategy which talks about blue hydrogen as an interim solution. But the costs of green hydrogen are expected to come down quite precipitously as a consequence of improvements in the technology for hydrolysis of water with the energy derived from renewable fuels, and the general pattern of experience or learning curves. So the main point from the LCOH analysis then is that blue hydrogen is going to be, in the longer term, is going to be the most costly option. And so by tying oneself into that option, one is likely to get sewed into or locked into or cemented into a high cost option. And I'm going to take up this point now of incumbency and pathway dependence and lock-in using the multi-level perspective. Those of you in the audience who have not come across the multi-level perspective as a framework through which to understand transition, it is an incredibly useful framework, and there's lots of work, lots of publications in the literature which you can access, and I particularly recommend those by Frank Ilse, but there are also many other authors. And the main point from the multi-level perspective is that energy transition is likely to happen as a combination of various factors, the first of which is the destabilization of the landscape, and we certainly are in that at the moment as a consequence of climate warming. The second is the challenging of the existing regime, and we know all about who the regime holders are in the sector. It's the fossil fuel industry, as a consequence of the niche developments, or what we call strategic niche management. Now, the regime is what I like to portray as this pentagon of science technology. So it's a fortress of science and technology, markets and consumers, cultures, policy, and industry, which becomes very difficult to dislodge. And I would even add that the mullahs are in some ways a representative of the way in which this regime has infused, if you like, our kind of thinking within the fossil fuel space. But this is a separate discussion, but the issue that I really want to draw out of this in terms of the blue hydrogen is that by establishing a blue hydrogen economy in South Africa, we will create a new regime. So if I just were to show you, this regime the fossil fuel regime will be replaced by a blue hydrogen regime, which will be even more difficult to dislodge. And so the danger of this strategy is that puts in place new pathway dependence, a new set of incumbents who will be difficult to dislodge, ongoing carbon emissions, high technical risk, and the likelihood of sunk investment, which will give us lock into high LCOH. All of those points I've already made. Of course, the arguments for blue hydrogen are clear right in the beginning. So the retention of coal mining jobs, a quicker transition, and in some ways meeting some of the just transitions concerns. So my final point here really is that in my perspective, coal is not the bedrock of our economy, it is the nemesis. And I think that this would be, obviously this is something that could be debated within this forum, and I look forward to ongoing discussions with colleagues and others on my perspective on this issue. But I just want to end with this slide to say that we are the custodians and not the creators of the planet, and we should be mindful of that status in any discussion about the future of energy systems, and particularly a discussion around what type of hydrogen would be most appropriate for the future going forward. Thank you so much, and I look forward to any further discussion.
Thank you, Prof. Round of applause. Thank Prof for sticking to time. Can we therefore take Elvis Avenyo to do our next presentation? Elvis is a senior researcher at UJ at the Center for Competition, Regulation and Economic Development. He has a PhD in economics of innovation, policy studies of technical change and governance from United Nations University in Netherlands. He researches broadly on development economics with interest, innovation, technical change, industrial development, labor markets, and firm behavior, with a focus on developing countries. Over to you, Elvis.
Thanks, Chair. So my presentation this morning is largely based on a joint paper with colleagues at CCRED, Jason and Julius, and the paper has also been published as an IDTT, Industrial Development Think Tank, working paper on our website. So a quick glance again at the forum's program does show that a key focus of our deliberations over the last day or so has been to sort of discuss several ways we could mitigate climate change. And this has to do with transformations in our production systems, which involves also the energy systems as well, from coal to whichever color of hydrogen. And then we have the distribution systems, and as well as sort of the consumption patterns that we do see having very important implications for our climate change. And at the core of some of these discussions, and for someone who is probably more involved in industrial development, a key question then becomes how to transform manufacturing, specifically industries and industrial processes from, let's say, very small stack industries and probably sort of industries that generate fumes into our climate, into a more greener industrial processes. And we've seen sort of over the course of the development of some of these issues, some emerging trends and some emerging evidence indicating that we do have sort of, we can leverage the fourth industrial revolution to try to sort of generate and reignite, particularly in South Africa, reindustrialization, but as well as trying to meet our climate objectives. But we do see that the evidence, particularly in the South African context, is often quite anecdotal, mainly because we have very little understanding of how firms adopt some of these digital technologies, but how they can adapt them into their specific production processes. So what we try to do, particularly in this paper, is simply to try to understand the specific factors that sort of underlie firms' adoption strategies, but as well as how they try to sort of mitigate some of the constraints they do face in the process. So to sort of understand some of these issues, we got together with some international researchers from UCL, from Argentina, from Brazil, and from UNIDO, to try to, first of all, to understand some of the fundamental conceptual issues. And what this framework simply shows is that we do know firms organize differently. And the process of organizing, they use different sort of technologies that have different dimensions. And these different dimensions also sort of define what these firms produce. So in that process, they adopt and sort of are influenced by different drivers and enablers that reinforce their adoption strategies. And we do see in the green arrow that shows that these strategies do also influence how these firms sort of perform in the short run, in the medium, as well as in the long run. And we do see quite frequent, keenly, is the sort of the issue around sustainability. And we do see also the sort of the feedback loop that does indicate that firms' adoption strategies, which are often very transversal, influences their performance behaviors, but also these reinforce how firms sort of adopt technologies also in the future. So depending on your school of thought, you probably would agree or disagree that we have four main sort of types of industrial revolution. And we are experiencing largely the fourth industrial revolution, which mainly focuses on digital production technologies. And what we'll be discussing over the course of the forum mainly has to do with renewable energy that features mainly in the current wave of the techno paradigm that we are experiencing. So our sort of work has been trying to reclassify some of these revolutions in ways that contextualize the real issues, particularly in the South African case. And you see probably in the subsequent slides that I'll be using mainly ways like sort of manual and semi-automated technologies that simply refers to the first two generations. And then we have the third revolution, which mainly focuses mainly on sort of the ICT related issues that we experienced in the previous revolution. And then we have the digital system enabled technology that focuses mainly on renewable energies, robotics, and additive manufacturing. Largely we sort of regroup some of these technologies, and what I'll be focusing on largely today has to do with sort of what we call the generations 3 and 4 technologies that mainly have functional processes in integrated and smart processes, and that this also includes what we are referring to particularly on as digital system enabled, but also this also includes for our purposes renewable energy. So as I've already mentioned, we've been trying to understand some of these issues at a very sort of granular stage. So what we did in collaboration, supported by the dtic, but also in collaboration with the South African Industrial Development Research Chair, is simply to undertake sort of a family level survey to try to understand some of these issues much better. So we conducted an online survey during the in the middle of the pandemic, so we couldn't sort of visit some of these firms. So we conducted online surveys trying to understand some of these issues in 3 main sectors: Mesita, the cheetah sector, as well as the textiles and fiber processing. So we've been trying, and this is also sort of work in progress. We've been trying to understand some of these technology issues from the sort of survey that we've gotten, particularly from these 3 manufacturing sectors. So a quick sort of a descriptive of the data that we got simply shows that currently we do see some heterogeneity in adoption behaviors of firms when we talk about advanced digital technologies. And we do see that South African firms, specifically on the firms that were responding to our interviews, are still quite dominant in the adoption of very manual and semi-automated technologies. But we do see some emergence of fully ICT and ICT related technologies emerging. But what is quite interesting as well is that we do see a very low rate adoption sort of behaviors in what matters now, which is largely the digital system enabled technologies. And when we look and break these down across specific sectors, we do see also some of these heterogeneities if even becoming more sort of pronounced. So we do see largely quickly on this, the Mesita being more a sector that's more having more affinity towards sort of advanced digital technologies, whilst we do see other sectors sort of lagging behind in the adoption rate. And when we sort of decompose our data into sort of size classifications, we do see as well that firms are largely also mainly using very manual and semi-automated technologies, but we do see specifically medium and large firms being more sort of attuned to sort of having characteristics towards the adoption of sort of advanced digital technologies. So we did this as well across different industries that or firms that are in a data set, and we do see quite a varying sort of characteristics emerging. But largely, the data still shows that firms are largely using very outdated technologies, but we do see some trends where that show that there is some emergence of the use of advanced digital technologies. But all hope is not lost. So what we also did in our survey is simply to ask firms of their future expectations and how they are reorienting their production systems and how they are expecting their production systems to change over a period of time. So we do see, in contrast, that firms have they are expected largely, and these mainly expectations. I think it's quite important to mention that their expectations are that they see their production systems moving toward fully automated and sustainable systems, but as well as we do see that the gray proportions have increased quite tremendously in the future, which is simply 5 to 10 years, right? So if, assuming that we don't have another COVID or probably another external shock, and firms sort of some of these expectations uphold, we would expect over this period that there'll be some improvement in how much advanced digital technologies firms use and how much advanced digital technologies they are integrating into their production systems. So based on that, what we simply did is trying to also to identify what specific factors influence these adoption rates. So we did quite very simple econometric analysis of adoption characteristics, and then we regrouped. Sorry, we regrouped our core characteristics mainly based on firm level characteristics, industry level characteristics, as well as SITA level characteristics into a group of constraints, I would say, that we identify in the literature, particularly, let's say, institutional related constraints and cost related constraints and among others. So all we do see emerging particularly is the issues around cost related constraints, right? And we do know on top of our heads that firms always have financial constraints, and they always cite sort of capital constraints as one of their fundamental issues they face in adoption of technologies. And we do see these also quite emerging strongly. What we also see is the question on skills. We identified that firms, and in sort of in our analysis, we do see that lack of skills, and particularly lack of STEM skills, also plays a very important role in constraining firms in the adoption of their technologies. And we do see some also other emerging sort of variables like export orientation that enables firms to adopt technologies. But also we do see that firms that have sort of foreign affiliations tend to have a higher likelihood of adopting advanced digital technologies. And we do see some of these sort of evidence sort of pertaining across specific business functions, but across also all the other dimensions that we analyze in the paper. So quickly to sort of also give you sort of a vivid picture of what we do see emerging in the data on the sort of the constraints questions, particularly on capital. We do see here that the capital question is quite pronounced, and it's quite pronounced across all the cities that we considered, particularly in FP&M. But what is also emerging quite interestingly is the lack of the skills question, which is adequate human resources, but as well as one other main factor that's emerging that we didn't see emerging quite strongly in the empirics, but we do see emerging in the descriptives as lack of awareness. So there are a large proportion of firms that are simply not aware of digital sort of technologies, and this is quite a problem, right? Sort of given the revolution. So we also further decompose that into the size classifications, and we do see sort of some distinctions or some heterogeneity in the specific problems that firms face. So the previous slide shows that the constraints firms face differ across specific industries, but these also show that the constraints firms face differ across specific types of firms, particularly in terms of like simply size, right? So these heterogeneities are emerging quite strongly in our data as well, and we do see some of this also coming out in the discussions that people have been having around some of these issues. And then we also try to see much more, trying to back the empirics with on the descriptive on the skills issue. And we do see that actually we do see that that sort of the STEM question is more pronounced in the empirics, but in the descriptives it's not. What is more pronounced is manual and repetitive skills, but also human-computer interaction skills. And this, we try to explain this by the fact that probably because firms are still more dominated by sort of manual technologies, they still rely on some of these manual and repetitive skills in order to sort of produce and perform their functions. And then quickly, one explanation we are getting from the data is simply the fact that firms are having some difficulty in sort of getting workers with STEM skills. And I think this has huge policy implications. So that these might actually be explaining some of the reasons why we don't see sort of the STEM abilities emerging strongly here. So in conclusion, our empirics that sort of provide some gradual understanding of some of these issues that are becoming bassy in terms of the discussion. And we do see that specifically digital industrialization could be fundamental for the structural transformation that is required, particularly in South Africa. But we see some inequality emerging across in the adoption and the use of digital technologies across firms, mainly because some of these technologies are also quite they vary in terms of their maturity rate, but as well as how firms apply them and the scale at which they apply them. So we do see likely that some digital divide may be emerging across sectors, across industries, and as well as across firm classifications. And we are sort of pushing that these findings have potential to influence some of the discussions we are having. And we do think that to sort of front some of these issues, we require very targeted policies, not very straightjacket policies, targeted policies that take into consideration some of the heterogeneities that we do see emerging from the kind of work we are doing. And this is largely a work in progress, and we are hoping to sort of have future iterations of some of the issues that we are talking about today. I want to end there. Thank you.
Before I invite Kathleen Bergh to the stage, let me just tell you a bit about her. She's a researcher at the Energy System Research Group. She has a background in chemical engineering, graduating from the University of Cape Town. She has an MSc in Sustainable Energy Engineering and received the award for the Best Master's Dissertation for Research in Energy Efficiency in the South African crude oil refinery industry. She has since worked as a senior process and plant engineer in the oil, gas, and refinery industry with Sasol and Total, both in South Africa and the United Kingdom. Her research interests include decarbonization, just a transition to a low carbon sustainable economy, net zero emission for business and industry, and climate change and carbon and sustainability strategy development. Kathleen will be on the line. Kathleen, over to you.
Welcome. Thank you for giving your time today to listen in on my presentation. I'm excited to present to you today some of the findings from the paper submitted, an analysis of the Secunda coal to liquid facility in the context of South Africa's energy transition. Unique to South Africa, synthetic fuel production from coal is the single major contributor to Scope 1 greenhouse gas emissions in the liquid fuel supply industry. The Sasol complex in Secunda, operated by Sasol Synfuels Pty Limited, is the world's largest commercial coal to liquid synthetic fuel facility. The Secunda facility converts around 40 million tons of coal per annum into around 150,000 barrels per day of liquid synthetic fuels, or approximately 5 to 6 billion liters of white fuel product per annum. This is jet fuel, petrol, and diesel. Other products include inter alia pipeline gas, pitch, carbon products, solvents, polymers, and other chemicals. And while I have your attention, let me start discussing some of the more technical part of the paper, the process of coal to liquid. So coal to liquid process includes the gasification of coal and Fischer-Tropsch processes. This differs from traditional crude refining in that coal to liquids is 5 to 7 times more energy intensive than conventional crude refining. Notably, the two Sasol CTL plants, which is called Sasol Synfuel in Secunda, encompass the single largest point source emission of CO2 in the world. So Sasol's greenhouse gas emissions profile is dominated by emissions from their CTL-based operations in Secunda, and these account for approximately 85% of their global Scope 1 and 2 emissions. Sasol Secunda converts coal to liquids in 2 steps. The first step is the gasification of coal. The coal is gasified with oxygen and steam under high pressure to yield a mixture of gases, mainly hydrogen, carbon monoxide, and methane. Bergh gasifiers using steam and oxygen process low-grade, high-ash coal available to Sasol. This synthesis gas is then fed to gas purification and is scrubbed with methanol to remove chemical byproducts, both available and not so valuable, which include sulfur, carbon dioxide, tars, oil, phenols, ammonia, cyanide, and other components. After being cleaned of impurities, the purified synthesis gas mixture sent to the water gas shift reactor, where the hydrogen to carbon monoxide ratio is adjusted to 2:1, which is critical for the Fischer-Tropsch system. This ratio is adjusted by the production of hydrogen and carbon dioxide. So this is where the bulk of the concentrated CO2 stream is generated. And once the CO2 has been removed, the syngas stream is then passed over an iron-based catalyst in the Fischer-Tropsch synthesis, combining hydrogen and carbon monoxide to produce a range of hydrocarbons, including motor fuels. So from a CO2 perspective, it is this carbon monoxide to hydrogen ratio that is inherently governs the excess carbon dioxide emitted. The water gas shift reaction converts excess carbon monoxide to carbon dioxide, and in doing so, this increases the quantity of hydrogen needed for the ratio. And steam reforming can be used when natural gas is used as a feedstock for the production of syngas, where methane is converted to carbon monoxide and hydrogen. So the gas purification step, as was mentioned earlier, the rectifier process separates out carbon dioxide from the feed stream to the Fischer-Tropsch reactors, and it's this concentrated stream of CO2 removed by the rectifier process that is emitted to the atmosphere, giving rise to the largest single point source of CO2 in the world, in addition to carbon dioxide emitted from combustion for process heat requirements. Today, Sasol Secunda Operations is the world's largest producer of grey hydrogen from coal-based feedstocks, and it is this hydrogen producing process that is responsible for around half of their greenhouse gas emissions. This is just a Sankey diagram highlighting the resource intensity of the chemical and liquid synfuel production process at the Sasol Secunda facility. The data is from the sustainability report in 2021. The left-hand side are the inputs and the right-hand side is what's produced. Just to note that the coal feedstock here of 17 million tonnes per annum reported is dry ash-free basis, but the actual coal consumption, including ash and water, is approximately 40 million tonnes per annum. You can see this as well because burning 17 million tonnes of coal won't result in 57 million tonnes of CO2, and also the data doesn't include the mass of doesn't include water vapor or steam losses, and emitting approximately 57 million tonnes of CO2, using 89 million tonnes of water, consuming 288 petajoules of carbon intensive energy, and generating 242 kilotonnes of hazardous waste. Sasol Secunda has significant environmental externalities. If the liquid fuel production chain or network is analysed, synfuel produced by CTL technology is inherently worse for the environment and climate than conventional crude oil refined fuel. Well-to-wheel analyses show that even with carbon capture and storage, coal to liquid production chain emissions are higher than for crude derived fuels. So the demand and supply dynamics of the liquid fuel industry are important to understand both inland and at the coast. Our country's abundant supply of low-grade coal enabled the establishment of government-funded synthetic fuel plants in the inland area adjacent to coal fields. This, together with South Africa's historic reliance on imported crude oil from the strategic significance that fuel products assume in all countries. Yes?
Apologies. People on the line are asking if you can share your presentation.
Apologies, you should have said that before. I apologize for that. So, as I say, the demand and supply dynamics of the liquid fuel industry are important to understand both inland and at the coast. Our country's abundant supply of low-grade coal enabled the establishment of government-funded synthetic fuel plants in the inland area adjacent to coal fields. And this, together with the reliance on imported crude oil from the strategic significance that fuel products assume in all countries, the consequent establishment of refinery capacity at the coast, some considerable distance from the country's inland industrial hub and major market for fuel product, has given rise to fuel industry characterized by complex locational economics. These in turn have given rise to a regulatory system and logistical infrastructure that respond in significant part to these geographic features. So South Africa has 3 conventional crude oil refineries situated at the coast and 1 that is situated inland. 2 coastal refineries, NREF and SARChI, have closed, leaving Astron offline for refurbishment as the remaining coastal refinery in the country. Sasol Synfuel in Secunda and Natref in Bergh are 2 refining facilities located inland and supply 100% of their output to meet inland fuel needs, which include the Gauteng province, the country's biggest contributor to GDP. The following table presents the crude oil feedstock capacity of liquid fuel refining facilities between 2010 and 2022, as typically stated, but the production of coal-derived synthetic liquid fuel and the refining of crude oil are 2 entirely different processes, and the terminology of quoting crude nameplate capacity of barrels per day for synfuel in the South African liquid fuels industry is relatively meaningless and obfuscating. White-oil products, namely diesel and petrol and jet fuel, that is produced from each facility is a better number to use in regards to the liquid fuels landscape. So the table on the left, meeting only 23% of the country's petrol and diesel needs in 2019, when all the domestic refining facilities were operational. Sasol Secunda's emissions intensive coal to liquids conversion process accounted for around 7.7% of national emissions, producing the same volume of 5.5 billion litres per annum. The table on the right, with only 2 facilities operational at the time of writing, Sasol Secunda and Natref, the country's domestic, the Sasol Secunda percentage increased to roughly 52%. And looking at South African liquid fuel demand, more than 60% of South African liquid fuel demand is spatially concentrated in 3 provinces: Gauteng, KZN, and Western Cape. Gauteng is the largest liquid fuel consumer at 9.3 billion litres per annum. The liquid fuels industry tends to refer to its demand sectors in terms of coastal and inland areas, mainly as a result to how these areas are supplied and managed, i.e. the inland areas supplied from Secunda, Natref, and the Transnet pipeline. Based inland, these facilities have more efficient logistical capacity to convey refined product to inland clients than their coastal facilities, a critical component of coastal refiners' operational requirements. Sasol also benefits from its inland locational advantage, being paid the full cost of the transport from the coast to market through the basic fuel price, whereas product is transported only from Secunda to Natref or Natref to market. Accounted for 21% of the feedstock supply for the South African oil industry. and 57% was from crude oil imports. Imported finished products accounted for about 22% to meet our liquid fuel requirements. South Africa is the world's sixth largest consumer of coal, as well as the sixth largest exporter of coal. In 2017, the South African synthetic fuel industry consumed 23% of all coal consumed in the country. And Sasol is also the hub of our country's chemicals industry. The synfuel sector serves as a source of liquid fuel and the country's major source of chemicals, feedstocks, and intermediates. The chemical sector contributes to around 3% of national GDP, and this includes liquid fuels in the chemical sector definition. It's also a large employer within the industry. Sasol's a large employer within the industry. So just to get a holistic view of the structure of the liquid fuels industry in South Africa, one needs to understand the pricing mechanism that governs fuel prices. And South Africa has a very unique liquid fuel value chain and a legacy of a very complex regulation that has undergone some reform. The regulatory legacy is also interwoven with an existing complex fiscal regime. The basic fuel price is regulated using the BFP mechanism, basic fuel price mechanism, and is related to the cost of purchasing petroleum products from international markets and the cost of related to shipping these products to South Africa. This cost is therefore largely influenced by the international price of refined products and the rand-dollar exchange rate, and is based on an import parity principle. So import parity principle is basically what it would cost a South African importer of petrol to buy the petrol from an international refinery, transport the product from that refinery, insure the product against losses at sea and at land, and land the product on South African shores. All other elements making up the petrol price are local in nature, and these include taxes, levies, margins, and storage and distribution costs. The figure shown here shows the components of the petrol price have risen over time. The Road Accident Fund levy has increased by 425% since January 2008, outpacing the general fuel levy, which was up 225%, and the basic fuel price, which is up 119%. The figure also shows the basic fuel price, which reflects international product prices and the rand-dollar movements predominantly, and that this fluctuates more than the general fuel levy and the Road Accident Fund levy. So in 2019 or 2020, the general levy generated around 80 billion rand for the government, and it's the fourth largest revenue stream. The top four revenue sources for the South African government have not changed for at least a period of 20 years. The money from the general fuel levy flows into the National Revenue Fund, together with revenue from all other taxes, and there is a portion of the general fuel levy that is specifically set aside and transferred to South Africa's 8 metropolitan municipalities. And in 2019 and 2020, this amounted to 13.2 billion rand. The South African government, through the IDC and PRC equities, continues to hold a 22% stake in Sasol, the world's largest producer of liquid fuel from coal. Subsequent to Sasol's privatization, the IDC remained a shareholder, although its shareholding has been reduced. The dividends received by the IDC contribute to the funding that the IDC invests in new projects and in fulfilling its development mandate. Just quickly, the top imports and exports over the period of 2018 to 2020, we can see from this trade data that liquid fuels, transportation, automotive, and mining sectors have the largest effect on the South African balance of payments and a significant impact on foreign exchange. As you can see, crude oil, vehicle parts, cars, and gold, platinum as some of the main imports and exports. With Sasol So the apartheid regime created Sasol to produce CTL fuels domestically and thereby increase the fuel security of South Africa under the regime at the time. This was driven by sanctions against South Africa during the 1970s oil embargo. Since then, government policies and regulatory mechanisms have cultivated Sasol and CTL fuels in South Africa. Large sunk costs and demonstrated financial benefits to Sasol since its inception have enabled the continuation of Synfuel operations. Approximately $19 billion in 2020's monetary values, today's value, was invested in Sasol 2 and 3, the Secunda site, in the early 1980s. And over the years, a variety of policy issues, such as historical subsidies and supply agreements, have been addressed. However, state support, largely through the mechanisms of setting the fuel price, which is based on internationally traded refined product, further enables the carbon lock-in of coal to liquid fuel production. And although historical subsidies to Sasol have been justified on the grounds of ensuring domestic security of supply, the pricing mechanism is unable to insulate South African consumers from the oil price shocks. And importantly, the fuel price has a direct influence on the cost base of our country's economy. The cost of production of synfuels and therefore the profitability of South African synfuels producers bears no direct relationship to the production costs of the crude oil refiners. Yet there are price takers or prices set according to international crude refining economics. Sasol estimates that the break-even cost of producing synfuels from coal is approximately $35 per barrel. However, the data behind these figures are not publicly available and therefore cannot be publicly reviewed. Coal to liquid is an energy-intensive multi-step process that converts coal to liquid fuels and also chemical feedstocks. The process requires a significant portion of carbon from the feedstock coal to produce hydrogen and generates electricity. As long as coal is used as a feedstock, the CTL process will remain fundamentally carbon intensive. And these are production process related limitations. So further significant improvements in the Secunda greenhouse gas emissions profile will require the introduction of lower or low carbon energy feedstock.
2 minutes.
Sure. Sorry. Finding an optimal transition pathway to decarbonizing liquid fuels, transport, and the chemicals industry is not an easy task. The country's economy was built on the backbone of cheap, abundant energy and feedstock coal, and our over-reliance on coal extends from power production to coal processing technology in the form of synthetically derived hydrocarbon, fuel, and chemical products. Deep decarbonization is required in these sectors. Quantifying the scale and extent of support that Sasol enjoys is an important first step towards the reform of production subsidies. The basic fuel price mechanism supports the liquid fuels industry, but consequently also supports the single biggest point source carbon emitter in the world, Sasol Secunda. At the same time, the state wants to implement a carbon tax, but the state is also a relatively significant shareholder of Sasol. There is a need for the basic fuel price to be reviewed owing to the differing cost structures between fuels produced from crude oil and fuels produced from synthetic fuel processes. And looking towards future technology change with electric vehicles and increased efficiency internal combustion engines, the tax collected from liquid fossil fuel will decline, which may put pressure on the state to look for alternative revenue streams. Other streams of government revenue should be explored to balance any future diminishing revenue from fuel levy taxes. Given that the synthesis technology is carbon capture and utilization compatible, it's conceivable that the complex can be transitioned into a fossil-free future. But this will require analyses beyond replacing the high energy demand of this process. From its current coal-based supply to renewables, the actual source of carbon itself will have to be reconsidered. And it's worth noting that shutting down or retiring the CCL facility in the liquid fuel supply sector has a mitigation impact comparable to the decarbonization of the entire transport sector. But however, this would have a disastrous effect on the current supply to the chemical sector. Repositioning Sasol technology and production towards a net zero future, as it has started to outline in its 2021 climate change report could be a more beneficial mitigation pathway than simply shutting it down. However, the continued subsidization of the single largest point source emitter in the world has to be questioned in light of the alignment of our country's greenhouse gas mitigation goals and commitments. Thank you, and apologies for the beginning.
Thank you, Kathleen. I think it's our fault. Apologies to also the participant online. Maybe I should do things differently. Let me allow attendees online maybe to raise questions. I'll start with them before coming to people that are here physical. I don't see any hands. Okay, let me come here. Maybe while they're still mulling over some of those things, I suspect that questions from here and then responses will at least provoke them, because we really want to have participation from both attendees. Can you open it here for anyone who has questions?
Morning, my name is Wendy Lelinda from Toyota. Thank you so much for both for the presentations, all three presentations. I just have one question for Elvis relating to the digital technologies adoption. Yeah, I think there were some really interesting findings there. I just wanted to ask, in your study, was there any maybe consideration or questions maybe in your surveys geared towards the employment implications of adopting digital technologies in the various sectors, especially if you look at your Mesita, your engineering sectors, and so forth? Because I know, when we're going on this reindustrialization journey, we talk to having high labor intensive, jobs and industries, or high labor intensive projects. But yeah, how does your study look to the employment implications, and what are some of the recommendations maybe that can be made in terms of having digital transformation also play a part in terms of increasing of employment as well? Thank you.
Maybe before you respond, can I also abuse my position? I might be standing between you and a lunch, but maybe, Prof, if I can come to you, I think the question that you also raised in your last, slide, to say that this, blue hydrogen is quite expensive to actually do, but can we afford just to immediately go straight into the green hydrogen without actually taking into account that whole transition, because it's going to be quite important. But I thought maybe, and it's also related to maybe to Caitlin, your question to say that we're still dependent, highly dependent on coal, but South Africa is not going to be able to afford to just completely move away from coal into blue hydrogen, because it's quite expensive. So I'm just trying to understand what has been advised, or what are you advising maybe government of South Africa as well to actually do, to actually, given the fact that it is quite expensive to actually move, to hydrogen. But Prof's also saying that, look, the blue hydrogen might be tapped into it. It's also quite expensive. You can't just go to the green hydrogen. So what should be the best, maybe, a position that South Africa should take on this one? Maybe to Elvis, the issue of digital technologies from, I think, the firm level survey. Do you think that maybe as CITAS, or maybe CITAS should start dictating to companies, maybe to actually force them to move much quicker into embracing the digital technologies in terms of the training or the skills that they actually are doing? Because if you're saying that they're still lagging behind in terms of embracing these technologies. And maybe it would be interesting to look at, maybe in future, when you say that you still go and look at other studies further on top of this, the impact of COVID. You did, the study was done, at the height of COVID. It would be interesting to actually see whether companies were actually able to embrace, digital technologies much quicker because of COVID. And I think those are the things that would be interesting to actually see. Whether it would be because of COVID or because of, ideally, there's 4R that is actually taking place, so therefore they don't want to be left behind. Let me stop there and allow our presenters to respond. I don't know. We can start first, Prof. Maybe go to Kathleen and then end with.
Okay. Kaemete, thanks so much. I mean, I think it's perfectly clear from what my perspective is that we shouldn't waste any time and effort on blue hydrogen. First of all, I think blue hydrogen is a figment of the imagination. There is no such thing as blue hydrogen. I mean, I'm sorry to say that so strongly, but blue hydrogen is in essence, the definition is the production of hydrogen with total carbon capture and sequestration. And the technology just doesn't exist, and it's certainly not economic. So to pin our colors to that mast, to fly that flag would be exactly the wrong thing to do. We, in any case, are moving very slowly on the decarbonization of our energy sector, and as Caitlin indicated, decarbonization of the liquid fuel sector. So why not just accept the fact that between now and 2030, we're not going to make much progress, but thereafter we should be in green hydrogen full stop, because it would be the most economic thing to be doing. So I just, I think in answer to your question, we should never contemplate an interim strategy of blue hydrogen. It's going to waste time and effort and divert necessary resources away what we really need to be doing, which is green hydrogen.
Yeah, thanks, David. I also agree with that. I think just looking at historically, we have cultivated industries by large amounts of financial support. Just Sasol Secunda alone had around $90 billion. Sasol 1 had about $4.5 billion in today's monetary value. So why not cultivate a green industrial complex and as you say, leapfrog to green hydrogen? And what are our enabling policies and financial requirements for that?
Okay, I hope you're not forgetting the answer to the question of Linda. Thank you, Kathleen. Let me go to Elvis.
Thanks. So quickly on the employment question, I think it's an important one, right? And it does often come up when we do see the emergence of new industrial revolutions, and this is also quite historical, and it's also a very historical question. But what is often observed, and I think there was a quote by, what is his name now? When computers were emerging, for instance, right? And it was like, we can see the computers everywhere, but not in productivity. What that means simply is we are not seeing the manifestation of some of these technologies in terms of displacement of labor, but as well as creating of new jobs. So my simple question would be that we don't seem to observe this sort of negative displacement effects of labor with the use of advanced digital technologies. But history also tells us that new technologies also create new sectors and probably also create new jobs. So I'm not particularly sure on the direction of the employment creation, particularly for these new emergence, for these particular sectors. But we don't see this coming out quite strongly in the data. But I do think that it's also quite a very important question. We should still be sort of exploring some of these questions. And then we do impact of COVID. So we do actually have an analysis that tries to see how COVID has affected firms' adoption of advanced digital technologies. And we do some of the evidence that we do see emerging is that it's actually created and made firms to be more resilient in terms of shortfalls in employment, but as well as on export activities. We didn't see much on sales, and then we didn't see much on export activities. But what we observe quite clearly is it enabled firms to be more resilient in facing COVID. And then on CITES framing, so CITES actually, I think by regulation, they are required to be training their firms. And I do think that one characteristic that's emerging, and that we saw in our data, is the lack, firms indicating that they have lack of information about advanced digital technologies. And I think that CITES do have a role, and of course, dtic also does have a role in trying to sort of develop training programs that enable firms and probably institutions that can enable some of these firms to be able to learn about digital technologies, but as well as know about the new technologies that I imagine. I think that would be very useful for their production processes.
Hello. Okay. Thank you so much for the really interesting presentations. I wanted to ask a follow-up to the blue hydrogen, green hydrogen debate, and ask about, okay, so if blue hydrogen is off the table, what does that mean for green hydrogen? And what about the water scarcity constraints? Because I think, South Africa is a water scarce country. Water's from what I understand, which is not a lot about blue hydrogen or green hydrogen, but my understanding is that water is a key requirement in that process. And so how do we kind of, meet the two constraints where actually we have a water scarce country and green hydrogen is going to need a lot of water? Is that really a sustainable option where we're going to experience increasing water scarcity in the event of climate impacts?
Thank you. I don't know, Prof. and Kathleen, who wants to take that one?
Caitlin, over to you if you would like to. But I mean, just to make the point that the water requirement is a tiny fraction of the water that we presently use. So we could generate sufficient hydrogen for the whole economy with a fraction of the water that we use on a daily basis. So it's really, water is not a constraint in the production of green hydrogen. What is a constraint is some of the other key input, which would be things like the catalysts and the graphite and the copper and the various materials that are required in the synthesis of the electrolysis equipment. So yeah, water is not an issue. If it were to be an issue, there's always the option of using renewable energy plus reverse osmosis to generate the water, which would be an additional expense, but it would mean that the water would be available, particularly at sites which are poorly serviced by rainwater. But it's really, in summary, it's really a tiny fraction of what we use on a daily basis within domestic homes. It's
okay, Prof, I think we lost you there, but I think we got a gist. The technology is failing us now. But over to you, Caitlin.
I think in terms of the green hydrogen and water, I think the benefits outweigh sort of the constraints, and in terms of where the water scarcity will be in the country going forward with climate change. I know KZN, we've got no problem with water at the moment, but yeah, as that aside, yeah, some of our processes are very water intensive as they are, and yeah, I think just requires a bit more analysis on where we will have these green hydrogen and electrolysis systems in the country to produce green hydrogen, where that will be. At the moment, industry does use a lot of water, so that will just have to be looked at a bit further.
Thanks. Another round of applause. Oh, there's a late hand. Over to you.
I just want to, sorry, my mic technique. I just want to pick up on this water issue. I don't think it's appropriate to say water is not a constraint. I think that we have to understand that when we make national plans, they land at a local scale, and their consequences at a local scale are very different. And the trade-offs that we might find acceptable or unacceptable at a local scale are different to those at a national scale, which is, I'm not arguing against a green hydrogen industry, the development of that industry, but I think that, and we do this when we speak about renewable energy as well, to just slide over the complexities because there might be pushback is not okay. We need to actually face up to the complexities of moving ahead with different industrialization strategies. And where some of the green hydrogen developments are happening, water is a very real issue. The water infrastructure is not working. And so I think we need to really take these these complexities into account. And, yesterday there was a lot of emphasis on engaging local communities and respecting local communities. And, and I think, how do we connect that participation and not just make it about feel good sort of processes that really don't influence policy at all, when we can say statements like it's not an issue or it will just be solved. When it comes to issues around like desalination and where it is being used in South Africa, we know that during the drought in Cape Town, desalination was used by the city of Cape Town as an emergency measure. That has been shut down because it was too onerous to operate. So I just think like this idea of when we have an idea about industrial policy, it will just happen. No, there are multiple actors who need to come together in a coordinated way with actually probably, for something like green hydrogen, unprecedented levels of coordination across energy policy, industrial policy, local development planning, fiscal policy, just transition planning. And I think it will just happen or it's going to be simple is disingenuous, and it's a dangerous way for us to advance any kind of policy in this area. And I think that honestly, this issue on water is like, it's critical. It's not true. And actually, yes, I would agree, a lot more analysis is needed. But those questions are being asked. And actually a lot of the actors who are asking those questions and who are quite resistant to some of these developments are resistant because no one's paying attention to them. And when they ask questions and raise questions, they get shut down and the complexity is glanced over. And so I think the question with these developments is like, how do we get to a yes that works for multiple stakeholders? And that's when we start to interrogate, not just at the national level of, is it good for the country, but also where it's happening, is it good at that scale as well? The just transition is a complex, multi-scalar challenge with multiple trade-offs. And I think unless we can get real about those trade-offs, and unless we want to look properly at the costs and complexities, we're just not going to get anywhere, which is where we are now. We're not moving. And I think that, like, I mean, everyone can agree, it's late even for us. We are so late to the game with so many things. And this is part of, I think, why.
Okay, on that note, Kathleen, I'll start with you to comment on that based on those views to say, look, indeed, it might not be important, but it is important, especially at the local level where obviously understanding is quite different, because if in KZN, you might not have issues, but Eastern Cape now with Nelson Mandela Bay, you do have issues. I don't know what your take is that on that. And then we can hand over to Prof after you.
Yeah, I agree with the question and the fact that it does require a lot of analysis, and there's multiple layers of complexity, and that's why these problems are difficult to solve. You've got the technical side, you've got social side, you've got the political side, you've got financial side, economic, and all of these aspects have to be brought together, and it requires multiple actors and decision makers. So yeah, I agree. It's the complexity can't be just brushed over, and yeah, I think case by case has to be looked at. So yeah, I do agree with you.
Well,
I didn't see the question, so I don't know the name of the person or who asked the question. But just to make a point that the question was, is water going to be a limiting resource? Not, is water going to be a limiting resource if the whole facility were to be located at Bergh where there is no water, or if it's to be located in an area where there's competition for water resources. And should it be done in a way that's going to override the concerns, the legitimate concerns and participation of communities? I would be the last person to suggest that this would be the case. So, I mean, I'm glad that the person who asked the question got that off their chest, because it's an important consideration, and I'm not greasing over anything or pushing something under the table and pretending it's not a critical concern. Of course, it's a critical concern. But the question was, is water a resource? And bear in mind that there's a lot of opposition to green hydrogen. One of the things that you frequently hear about is that we can't do green hydrogen in South Africa because we're a water scarce country. And no one's even sat down to do the numbers. How much water do you need? And what is that as a proportion of our daily water consumption? So that was the question. That is what I was answering. It has nothing to do with whether I was overriding community concerns in areas which are very water sensitive or not.
Okay, no, thank you. On that note, we are now, I think at 12:36, we way past our lunch, but I think we'll speak to the organizers as to allow a bit of time to have our lunch. Thank you to our presenters, and then can you give them a round of applause? And